Yeah, cool to be here again on the stage, second day. At least it's a little bit warmer and still not too warm. I mean, yesterday in the morning, whoever was here, it was a bit chilly on the stage. And people weren't able to follow my talk because they were asking if I were able to, how can this guy walk with barefoot when it's so cold? And it was completely distracting for most of the people. Okay, today is not that distracting. I try to distract you with that one. But first, a confession. Well, if you expect the latest, greatest, coolest, deepest secrets, sorry, I'm not an expert in that topic. I picked that up a while ago, so I would call myself some kind of curious apprentice with a bit of experience in there. But what I figured out when I started learning this topic was you will get flooded with tons of concepts, and you have no idea what they mean, why they're needed, how they're connected to each other, and what's the sense of all that stuff, and trying to sort that out. And nobody really explains it. So the blog posts assume that it's in there. In the books, it's somewhere buried, but it takes eons until you figure it out. And so you mix it all up. And what I try to do in this talk then, I said, well, I have to create a talk to make it for other people a little bit easier to pick that topic up. So trying to connect these topics and what they mean and why we need them and so on. So that is a little bit easier for you. And I said, can't be that hard to put that in a 1 hour talk. Yeah, I always forget that it's 40 minutes, which is just another little complication. Sorry about that. And then I figured out and said, oh, wow, it never fits in there. So just breadth or depth or just the concepts or the code. And what I tried is get a little bit of a compromise, so leading you along the way that your reasoning goes, so a little bit of the concept, and then going down to almost to the code. So I show you an example where you can read the code read up the code afterwards then, but we don't have the time for that. So basically, expectations, yeah, going through that. Yeah, and losing fear of math, of course, because, yeah, it's just formula. So these are humans too. They just have a strange way to express themselves. So, but bear with them. It's quite understandable if you look at that for a moment. And so I hope to spark a little bit of curiosity. But before we go into the details, just a little bit of motivation. Why should we care about reinforcement learning at all? So just a few success stories. I mean, 2013, DeepMind came up with an agent which was able, just by seeing this pixels from the screen and the number which represents the score, to play Atari games. 2015, they more or less perfected that agent, which was able to play all these games in a superhuman way, basically. 2016, we all know AlphaGo then, beating the grandmaster of Go. 2017, the next iteration came up, and which was able to learn Go without looking at anything what humans did, but just playing it against itself. And then at the same time, basically, the guys from OpenAI, they created this Dota 2 agents, first 1 versus 1, and currently version 5 versus 5, so 5 players versus 5. Playing and being really good. So 5 versus 5 is still a little bit of struggle. And the DeepMind guys at the same time mastered StarCraft 2. And if every one of you ever played that, now there's a lot, it's quite complex, these games. So there are a lot of degrees of freedom in there. And yeah, probably next stories will come up and say, yeah, well, it's just games. Why is it important? And it's not only games, so if you really look deeper into that, they also do a lot of impressive stuff with healthcare or with banking or with energy management and all that stuff. But the key point for me is, do you really think that a typical white-collar job has more degrees of freedoms in decision than StarCraft 2? From what I know, not really. And even if we're honest to ourselves as software developers, I mean, 80% of our job is sort of routine. And 20%, yeah, that's really hard stuff and creative and so on. But 80%, yeah, well, more complex than StarCraft 2? I don't know. And so I think that reinforcement learning has a potential to affect white-collar workers of all times in the future in a similar way how robots affected the blue-collar workers some decades ago. And we don't know if we end up there, and there are still a lot of question marks around. But I think it's worth having a look into that for that reason. Okay, let's have a look into it. What is it? Core idea. And then you go into these blogs or books and so on, and you see something like that. So reinforcement learning, agent, environment, policy, expected cumulative rewards, and you stand there, what the heck they're talking about? I mean, there's so much jargon in that I have no clue about what they mean. So let's start from scratch. So the core idea is we have some agent, some program, which interacts with an environment. So it's something it lives in. And it's got a task to solve, like winning the game, which we have seen before, or something like that, or not even winning, but something else, which makes finding the right medication, or whatever, making good trades in banking, and. And yeah, say, yeah, well, and I should learn that, and there's so many degrees of freedom, I have no clue where to start. So my problem basically is, can I model that in a way that it's easier to learn how to solve that task? So which makes it easier to place an algorithm on top of that. And people thought about that, and they came up with these ideas from learning theory, especially most of the times operant conditioning. Operant is an ancient term for effective, basically. It's the idea of learning a desired behavior based on rewards and punishments. And as punishments sound so negative, which is not widely accepted, we call it negative rewards. Well, it's semantics, but basically, yeah, well, that's it. And so we end up with a different kind of interface if we apply that. So agent environment, and we can observe a state then, basically, and we can send some actions to the environment, and then we get a reward for that. And our task basically simplifies to maximize the rewards that we accumulate over time. Be aware that this is a big simplification of a general learning task. I mean, we get a very narrow interface. We assume that it's always possible to represent learning or what we want to learn simply by a number, by a reward, and that's it. So, so whenever you go into reinforcement learning, be aware you narrowed it down right here. So there are different approaches available, and probably we have to look for some of those. Yeah, we talked about that. So our observations, so we limited the approach because it's quite easy to generate a learning model on top of that. But it has a downside, which is modeling this interface becomes really hard. I mean, it's a very narrow interface, and so resiliency is basically gone. Usually a resiliency in the natural environment is that we have different places where we get information from, and that we have different ways of showing our actions and so on, and observing states, and we just have one. And if we don't get this one right, what we see or what we send, it's screwed up. We don't learn anything. And whenever you go into reinforcement learning, you will have to deal with that quite a lot. Because representing your environment will, most of the time, kill you a little bit. Okay, so much about the what. Now, we are computer scientists. We're curious about the how. That's what's fun. And so, 6 questions. And that's probably time's already over anyway. First one, again, let's revisit that one. Learn the best possible actions is our task to maximize the rewards based on the states that we've seen. So, yeah. Okay. And then the first question we have is, yeah, where do states, rewards, and possible actions come from, actually? Yeah? Zip. Falling from heaven. And what we figure out, so how do we get them from the environment? And actually, people lied a little bit. So there's always a model in between. So some abstraction of the environment, which gives us the states and the rewards, and where we send the actions to, and yeah, and the rewards solely come from the model. So actually, the agent never actually interacts with the environment. I always ask myself, where's the model coming from? But that's a little bit like in Scrum. So start prioritizing your backlog. Where's the backlog coming from? It's there. Oh, yeah, that's always how my projects start. There's a perfect backlog there. And it's a little bit like that here. So there's a model. Where's it coming from? I don't care, there's a model. So yeah, you will always be faced with this question then, where's the model coming from? And if you're the person who is in charge to create that model to represent you, have fun. Anyway, so we have that model, yeah, makes it manageable, makes it a lot easier. Quite important, I screwed that up for a long time until I really understood that. The model is not known to the agent usually, so it's a completely separate task, building the agent and creating the model. So there are a few places, like in dynamic programming, which is a specific variant of reinforcement learning, where the agent knows the model, but usually you don't know it. So, and now, not knowing the model, but we have to make sense of that thing somehow as an agent in order to learn good actions. I mean, we always have to try to make sense. If I observe that state and send that action, what reward do I likely get from that? In which new state will I end up when I do that? And I have to represent that for myself in some way, because otherwise, I can't place an algorithm on top of that. So I go to the friendly mathematician next door and ask him, I have that problem, what should I do? And the friendly mathematician answers then, use a probability distribution function. So if you have no clue what's going on, attach probabilities to the actions. And we end up with something which looks a little bit daunting, but it's quite straightforward, basically. It just says, yeah, it's a probability that if we're in state S and use the action A, that we end up in the new state S dash, and then and get a reward of R. So, which is a number, basically. Yeah, that's basically it. But again, another simplification which in there, because that's MDP, Markov decision process. A lot of math, very confusing if you read it the first time. But basically what it says is, it's sufficient that you just look at this one state to be able to decide what action to take. You don't have to look to the history of the states, what happened before. Just look where you are, and it's perfectly fine to decide from that. I mean, that's the core of Markov decision processes. Again, a simplification. Because if you really listened to Dave Snowden this morning, and ordered systems, that works. If you go into the complex system, you observe a state and then apply a series of actions, you may, in 2 times, you may end up in very different places because they have a history. So for modeling complex tasks, this is not sufficient. Just have it in mind. For any kind of complicated, so ordered task, it works. And you can do nice things like calculating expected rewards from that and so on. But, well, now we have a way to make sense of that model thing, so that we have a way to reason about that. So this probability distribution function. Now we still have to figure out how do we reason about our own behavior as agent. And I mean, we want to learn the best possible action. So mathematician still next to us and says, sometimes mathematicians are a little bit lazy, which is cool in some situations. Give us the same answer. So first time we're not sure if that guy really listened to our problem or not, but yeah, even after re-explaining it, said, yeah, I mean it, use that. So, okay, so we create something which is called a policy. And this policy is just a probability that if we observe a state S, that we execute action A. Yeah, or if it's deterministic, yeah, then it's not a probability, then it's just, here's A if we see S, period. So probability of 1. Okay, now we have these 2 things. We can more reason about our behavior, we can reason about the model. Now, but how do we learn from that? Now we have all the basis to put an algorithm on top of that. How can we learn a good policy? And now, yeah, sorry, I'm a consultant for way too long. So it depends a bit. This is a bit tricky. There are a lot of approaches around, like here, like model-based versus model-free. So model-free is the usual case. We have no clue about the model. Model-based is, yeah, we really know the model. Or value and policy-based, we will talk about that in a minute. On policy, off policy, on policy, whenever we do make some predictions, we look to the policy we currently have. Otherwise, we forget about the policy, have and use some other means like greedily acting or something like that. or then having a whole episode, so a whole task or series of actions and states and rewards till we hit a finite state, that we look at the whole series before we decide how to learn, or if it's enough just to look at a few steps or just one step. And then do we look at all variants, full backups, or is it enough just to look at some variants, so some sequences that we look at, and a lot of variants. I will talk about two, probably because of the 40-minute problem, just about one variant and quickly, briefly touch the other one. But okay, let's dive a little bit deeper from here. And the variant I picked, because it's quite easy to learn from that or understand the basic concepts down to the code, is Monte Carlo. So model-free, value-based, on policy, deep backups, sample backups. Yeah, well, okay. But let's go to the task again. So we try to maximize the rewards based on all the simplifications we made before. So we try to maximize the rewards. Now, mathematician, of course, says, yeah, if that's our goal and we are somewhere in playing an episode, so we can't influence the past rewards we got, but we still can make a guess about the future rewards we get when we take a specific action. And then mathematician says, yeah, well, let's model that one, make a definition for that, for these future rewards. That's called return. They use, of course, because it's obvious, they use the term G for return. G, return, G, return. Okay, it's gain, basically. R is already taken by reward, so they had to use a different character. Okay, but it's G. So return is basically the reward we get for the next step, and then a discounted reward for the step after that, and discount. Just stop. Discounting? What's a discounting? So yeah, that's gamma, that's between 0 and 1, and yeah. So why do we need that? And mathematicians, they're cool sometimes, and said, yeah, well, sometimes probably it's a probability distribution, so your future rewards have a lower probability, so it makes sense to take them a little bit not so much into account. And then assume that you have infinite episodes, that there's no terminal state. And then no matter what action you would take, your rewards would add up to infinity. So you couldn't learn anything about that. So let's limit the window that we still can see from rewards so that we still get something reasonable where we can learn something from. And then you can also control how greedy or foresighted your agent acts. So for some economical leaders and political leaders, you always have the impression that they go with a discounting factor of 0, so just looking for tomorrow, and after that there's nothing, but that's a different discussion. Let's skip that here. Okay, you say, yeah, okay, now I have defined that one. What am I going to do that one? I still haven't learned my stupid policy. Say, yeah, just give me a second, says the mathematician. We take a little detour, because directly learning is a little bit harder, but maybe we can look at the behavior of that model and interact with the model over and over and over again, and then take that, whatever we get from that, and create some kind of a value function, which gives you some idea about how valuable it is to be in a certain state, or how valuable it is to take a certain action if you're in a given state. And we call that value function. So basically, it's an expected value. So if you take all variants of paths that we can go, so again, probabilities, not deterministic, then we would end up at an average of basically this value for a given state. Or the Q function, that's where Q learning comes from, and deep Q networks and so on, basically, is then looking at state and action combination. And you say, yeah, well, now I've got this detour. Here is my probability distribution function of that model, and now I'm able in some mysterious way to derive that value function here, which says how valuable is it to do this, because I figured that out somewhere over there, and then I can derive the, I still don't get it. Well, that's trivial. That's when I hate mathematicians. I say, yeah, it's straightforward, because in value-based learning, the optimal policy is the policy which gives you an optimal value function. So basically, if I'm able to figure out a value function where the value for each state is bigger than for all other variants that you get, so having other policies, that's your optimal value function. And the optimal policy, of course, is then this one policy, which gives you the optimal value function. And same true for the Q function. And then mathematicians, meanwhile, a little bit tired, says, yeah, well, that's it. I've solved it. QED, so quod erat demonstrandum, and I'm done. I'm out of here, going home, takes a drink, and is happy. Well, but we are not happy because we haven't still coded anything. So how can we implement that stuff? So we asked somebody else who hasn't had a drink yet and said, yeah, how can we do that, learning that policy? I said, yeah, well, there's a neat little trick in there, and it's called generalized policy iteration. Because what we've learned is learning an optimal policy, that's quite hard usually. So many degrees of freedom, we don't want to do that. We want to get close enough, basically. That's good enough. So sort of optimal policy. And what we figured out is, there's a lot of math behind that, but so some other mathematicians, but what they said, what works for some reason is we start with a completely random policy. So we just say, yeah, do this and that, and I don't give a damn what's happening there. And then you take that and evaluate the policy. So basically, you create an estimate for your value function. So you play a lot of episodes over there, and then you sort of figure out how valuable all these state and action combinations are. And then you look at that and say, well, looking at that, this action in this state is the best one, this action is in this. And so greedily update your policy. And then you repeat until your policy does not change anymore. And that's basically the optimal policy. Close enough. So basically, you don't really calculate the Q function, you calculate an estimate of the Q function. That's what you're doing. Last thing left in here, so yeah, that makes a lot of sense, but how do I actually evaluate that policy? How does that work, this step in here? Because that's still something I'm missing until I can write code for that. I say, yeah, use Monte Carlo. I say, no, I don't want to go to Monte Carlo. Say, yeah, you want to go there, but I mean something different. Monte Carlo is basically nothing but an umbrella term for a class of algorithm. Whenever it's unfeasible to numerically calculate an exact result, then quite often the mathematicians say, yeah, well, let's use a different approach. Let's use a lot of samples and then try to extrapolate the actual result. So create an approximation for that, an estimate for the actual result. And that's basically what Monte Carlo means. That's the whole secret behind that. And so, yeah, and here Monte Carlo means basically we play a lot of episodes. And for making sure that we see a lot of the stuff, we start with a random state and a random start action. And then we apply the policy until we hit a terminal state. And we store the information that we just gathered, so state, action, reward, blah, 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 until any terminal state. And then we can backwards calculate the return for each of the state action combinations we've seen, because the second last one is just the reward for going to the last one. And then we can discount that one and then take the reward before into account, and that's the return for that one. And going back to the beginning. And then what we still have to do is then we store all these state action reward combinations basically in a list. So for each state action pair, we store all rewards we have seen. And now think about the definition of the Q function. The Q function is nothing but the expected value for the sorry, it's not the reward, it's the return. I mix it up too, sorry about that. So it's really the return. So for all these, we store the returns for all these state action combinations. And then expected value is nothing but an average. So we take everything we've seen so far for this state action combination and create an average. And this is the estimate or the approximation of our Q function. And that's how we do this step that we had, this evaluation step for the policy. Yeah, and if this change in the Q function we call small enough, so adding more samples doesn't change a lot anymore, so becoming smaller than a given threshold, then we stop and update our policy and repeat. And if we do that, then we end up with some pseudocode like here. That's a book from Sutton and Bartow, which is a good book about reinforcement learning. And basically, it's exactly what's in here. So if we read that, yeah, we start with a random policy. We don't care about Q anyway because we override that as soon. And then we have that list or these lists for all the SA combinations, state action combinations. And we just start here. And actually, we don't loop forever. We loop until we get close enough, actually. But they were lazy when writing it down. And so, yeah, we choose a random start and action. And then we generate an episode. And then here, be careful, we go backward from the end to the beginning and just calculate the return for each of the state action pairs, store them. So we only store the first one, so the first one that appears because it has the highest return usually. The other one, if we see a state action combination more than once, we forget the other ones. Makes things a little bit easier. And we append that to the list, we average the list, and yeah. Okay, that's already an optimization because they were lazy again. Because usually if we do that all the time until this Q function is then good enough, yeah, that's quite a lot of. It takes a while, and then after that, we only can update our policy and then begin from the beginning, and then so on. So it would be two nested loops. And what people figured out, weren't mathematicians, were computer science guys. They figured out if we just calculate one episode, and then after the one episode, without waiting to really to converge here, we already update our policy. It converges a lot faster. The mathematicians said, stop, 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 we have to prove it, and they were not able to prove it yet. But it works. They are annoyed like hell. Mathematicians hate when they can't prove things and it still works. So if we ever want to annoy a mathematician, do something which you know works, but they can't prove it. That's cool. Anyway, so that's basically what I said here with the slow convergence. So they already optimized that thing, but that's just a detail. Basically, that's how it works. And there's one more thing that I want to mention, because it's a term that you also will hear a lot of times. That's this explore-exploit dilemma. And the problem is, if you just go along your policy to play episodes, there will be a lot of state action combinations that you will never see, because your policy says, well, don't go there. And especially if your pair policy is initialized randomly, you have a little problem with that, because you don't explore the whole space. And then basically you have to figure out a means to explore the whole space. And that's here the exploring starts. So starting each episode with a random state action pair and then following the policy. Another variant would be epsilon greedy, which you will also hear when you dive into that. Epsilon greedy basically says, follow the policy in most of the cases, and if a random value between 0 and 1 is smaller than a given epsilon, then do something random. So once in a while, do random action. And that's your explore-exploit dilemma, because usually you have to explore the place, but you want to exploit what you, maximize the returns that you get. So exploit the scenario. And if you download the slides and go to this URL, you will find a little Python program that's from a training course. It's added material from a training course. And you will find here a program which basically is exactly what you've seen on the slide before. So if you have understood the slide before, you go to that code and you just say, oh yeah, that's clear. So it's straightforward, it translates straightforward. In Python, it's quite straightforward, because with NumPy and all that stuff, that's basically you see the mass formula ahead of you if you use that stuff. Okay, so went down from core reasoning to the close to code level. What else? Let's just briefly give you 3 more things. I won't go into the detail of this concept, but this is the most widespread learning method. It is temporal difference learning. There are also variants of that. The big difference is this one, shallow backups. So it doesn't need to calculate whole episodes to learn from that, especially if you have infinite episodes, so where is no terminal state in there. It's a little bit hard to wait until the episode terminates before you start learning. So you want to have something else. And so some mathematicians also made their mind up, said, yeah, how can we do that? And Richard Bellman did a decent job in the 50s by doing all these Bellman equations, and there's a lot of magic in there. But the interesting part of that is that he said, yeah, well, we can represent the value function recursively. So value of a given state is the reward for the next action plus the discounted value function for the resulting state. Same for the QA, for the Q function. And so if you really think about that for a moment, it sounds a little bit weird. So, because this Q function is nothing but an estimate. So we can use an estimate to estimate an estimate. I found it a little bit strange. But anyway, for some reason, I'm not sure if the mathematicians were high or if they really were brilliant, but they were able to prove that it works in quite a lot of situations. So what they came up with an algorithm which just says, okay, I start with a random policy again, and as with a random value function also, and then I just say, okay, I do one step, and then I look what's the reward for that step. I take my estimate, which is nonsense at the moment, and add that to that step, and then use that with a learning factor to update the state before, the state action pair before. And we do that a lot of times, and for some reason it converges. Don't ask me why. It does. So again, they proved it, that it does in most situations. And that's quite nice and feasible, because now you have a way to learn all the time with every single step. And that's temporal difference learning. Again, a lot of variants available for that, but we leave it here. That's so-called TD0. TD lambda would be too much for today, so let's not dive into that one. Yeah, so yeah, okay, now we have done, we have these two variants and so on. What's all these other concepts that we heard about? And I mean, for instance, we haven't talked about anything like deep neural networks. I mean, deep reinforcement learning. That's the cool shit, isn't it? And when do we need that? So is that completely different? No, actually it is not. Because when do you use that? If you have very large state spaces. I mean, have in mind, if you have this representation of this value function, which is all the states, all the possible actions, and here are all the returns in there. That's your estimation. And now just assume an input data like an image 1,000 by 1,000, each one, 3 colors, 16 bits. So 65,000 times 65,000 times 65,000 times 1,000 times 1,000. That's your space, just this one. Have fun fitting that into your computer. And you don't want to do that. So, and you say then, it's an estimate anyway. So maybe I can use an approximator for the estimate. Yeah, I know it sounds strange again, but it's how these people think. And where can I go to get a good estimator for that? Yeah, neural networks. These are great function estimators. I mean, that's what they're really cool. Estimating quite complex functions. So we just replace this table with deep neural network. State actions in, expected return out, basically. And then we can use the traditional methods of deep learning to train this network. So create a loss function from that, expected return, and then so what we have in the Q function, so what it spits out, minus the actual return that we've seen, and then use a gradient descent to learn that, and so on. Quite straightforward stuff then. Okay, if you have understood deep neural networks, which would be another talk, which wouldn't fit into 40 minutes. Sorry about that. And that's basically, it's not totally that simple, so you need a few more tweaks to really get these deep Q networks and how they're all called, because there are some things in between that this total naive approach, it doesn't work all the time, and so you have to add a few more tweaks. But that's quite straightforward if you've got the basic idea. Last thing, before we more or less, or last concept I want to mention is this policy gradient learning, because you will stumble on that anyway when you go for reinforcement learning and try to dive deeper into that. And policy gradient learning doesn't make that detour across the value function. Because, I mean, in the end, what we're trying to learn is a good policy, not a value function. The value function is just a helper to figure out a good policy. And there are situations where it doesn't make sense to learn the value function, or it's not feasible. For instance, if you have a lot of actions, or even a continuous set of actions, so like an analog lever or something like that, which you can, because you try to create a probability distribution on that for creating your policy, it doesn't work very well, so to create a value function on that. So, and you say, yeah, let's learn directly, let's not make that detour. And what you do then is, basically, it took me a while to understand that crap, to be honest. So you take that policy and you add a parameter theta. I said, what the heck are you doing with this theta? I don't get it. Basically, that theta is just the configuration of your policy, so how it will respond if you see some state, which action it will probably pick. So, and theta is not a single value, it's usually a big vector or even a tensor or something like that. Have that in mind whenever you see just theta. And then what you're doing here, after you have this configuration parameter, or configuration parameters for that, then you can use something like policy as like a gradient ascent to learn that. So ascent, because we try to optimize, we don't want to minimize a loss function, we want to optimize the results. And there are a lot of algorithms that you will see, like reinforce, which is sort of Monte Carlo directly applied on that, or actor critic, which is sort of a TD learning variant, and so on. And we can also easily extend that to deep neural networks, where your policy becomes basically a deep neural network, and theta will become the weight tensor of your neural network. That's it, basically. And okay, we went through a lot of ideas and concepts, and we try to dive a little bit deeper. And there's a lot more, of course, to that than I just were able to talk about in the last 30-something minutes. So, last question is, okay, Uwe, I believe you, that's cool stuff. I got lost 20 minutes ago, but that's okay. But I want to dive deeper into that on my own. Where can I start with that? My own journey without you confusing me, okay? You tried your best to make these concepts fit into each other and make clear why we need it, but again, was way too much. So I want to do that on my own. And yeah, there's no one size fits all. Probably you learn differently, I do. But I give you the idea how I did that, and figure out your own one. So my recommendation is then start with some foundations. I mean, some people love to start with coding without understanding anything. I'm not a big fan of that. I really like to have an idea at least of what I'm doing before I apply it. And so there are some nice blogs where you can read in there. I mean, you had the terms from me now and how they relate to each other, so it should be a lot easier for you if you didn't get lost in 20 minutes ago to pick that up than it was for me. There are a lot of good online courses, so go for Coursera, Udemy, and how they're all called, or go for a book like Sutton and Bartow, Deep Reinforcement Learning. But please don't read all of that, especially not the book, just the basics, and then start some coding. It's very important, so to get a hold of that. So, by the way, you also find examples for all the other stuff like Q-learning and so on, and next to the example where I gave you the link for. And here they are quite nice. The online courses also give you nice exercises. And then you can also go to OpenAI Gym, which is really nice because they modeled all these, or they created all the models for you already. So you just have to create the agent, which is cool stuff, basically. And try some simple examples there until you get the hang of it. And then go for the next iteration. So say, okay, now about these deep reinforcement learning thing. So read some other blogs, do some courses again. That's what I did. Go, for instance, for here, Goodfellow and Yangguo, the deep learning book, which is cool, which is really cool, or Lepan, who wrote a book with lots of code examples in there. The reference will be on the end of the slides. So, and when you download them, you have all the links to them. And there's a lot of stuff where you can go through. Again, especially that one is a math killer. So don't start with that one. So give yourself a little bit of time until you dive into that one. And then go back to OpenAI Gym, try the ones that you did before with using some deep neural networks. Probably it won't run on your machine anymore right now because deep neural networks consume a lot of compute power, so probably you need to have an instance on some cloud provider or something like that. The other stuff you can still run on your machine then. And then trying some more advanced environments like the Atari environments, which you also get from OpenAI, which is really cool. That's basically where I am at the moment. So I said I'm not an expert. And then you can go on, complete the book eventually. I didn't also read them completely. Some advanced courses, some more research papers. Okay, I already read some papers, but I still have to make sense of them and so on, and maybe implement them. And there's some also likewise other environments like the WizDoom environment where you have a Doom simulator for reinforcement learning, which is a lot of fun, trying to figure out that, but do that later. And especially, you need some cloud instances, which hopefully your company pays for or something like that, to really make sense of all that and really implement all that stuff. But basically, that's what I brought for you. I hope I was able to give you an idea of not all just code examples, but what these concepts are about, how they fit together, what they all mean, and and how you can create a chain down to an implementation level. And then, again, giving you some more resources. Hope you will pick it up because it's fun. Actually, it really is. So here are the resources. You can download all that stuff from the Speaker Deck account from me. I will upload that tonight or tomorrow or something. I will send a tweet about that, or just look on Monday, then it will be there. And that's close enough. And yeah, that's what I had for you. First of all, thanks for your time and your patience. I'm totally surprised I made that in 40 minutes. I have no clue how that worked.
We have time for a couple of questions.
Yeah.
Are you up for it? We have two. These are the two we shall answer.
Okay.
Updating policy directly based on rewards could lead to a stuck in suboptimal local maximum. Is there any good practice to go through uncharted ways to avoid this?
Oh, that's the expert question, isn't it? Yeah. Usually, what I know from the neural network stuff, where we also end up quite often in local maximum or local minimum, no, depends on the direction, is that you create some noise which raises the probability to jump across that hill of that local minimum and then find a global minimum. But it's all, tricky, to be honest. So no easy way out that I've seen yet.
Okay, Anne, can you see any future of using quantum computers to speed up machine learning? They seem to be great with probabilities.
Isn't that Holly Cummings who was here for that question? Or the previous talk, basically, yeah. To be honest, I have a very, very rough idea about quantum computers, but I'm definitely not deep enough into the material that I could give you any serious answer about that. And before I start talking complete crap, I better stop talking. So good. I'm not sure.
Okay, that's a good life role. Big round of applause for Uwe, please.
Okay.
Bigger. Good.
Okay.